Welcome back, everybody. Today's video is going to be covering similar polygons and triangles. We're just going to go ahead and start off with the definition of a similar polygon. Basically, it just means that they are two shapes or multiple shapes that have the same shape themselves, but not necessarily the same size, right? And there's two things you want to know about similar polygons. The first one is that in order for figures to be similar, they have to have corresponding angles that are congruent. All right, and then they also have to have side lengths that are proportional. So the matching sides have to have equal ratios. And then the second thing you want to know is that the symbol for similar is this little symbol here. It's basically like a congruent sign without the equals part underneath it. So anytime you're writing a similarity statement, you're going to use this symbol, or you might even see it in some of the directions on our assignments. Okay, we're just going to start off with a basic example here. It says I've got two triangles and I'm going to go ahead and see if they're similar by checking their ratios, and then we could write our similarity statement. So assuming they tell you that the angles are congruent, because remember that was part of our definition of similar. So we've got angles here that are congruent, 1, 2, 3. Then we can look at our side lengths. So we want to match up sides. So GH is going to go with PT. I'm going to write that as a ratio. Remember, ratios are fractions, so 6/3, which reduces to 2/1. Then I'll do the same thing with HK and TQ. That's 6/3, which reduces to 2/1. And then on the third side, GK and PQ. If I write that, I get 9/4.5, which reduces to 2/1 as well. And so notice that every single one of those ratios is the same, 2/1, which automatically means these are similar triangles. And then we could go ahead and write our similarity statement, and that would look like this. Triangle GHK is similar to triangle PTQ. Now, one thing to be very conscious of when you're writing similarity statements is that the order matters. All right, so the order that you put your letters has to be matching in both. So G was the same as P, so they had to go in the same places. H was the same as T, so they had to be in the middle, and so forth. You want to make sure you go in the same order each time. And that's it. So check the ratios, check the angles, and then if it's similar, write your similarity statement. The next example is where we're just going to be talking about scale factor. Scale factor is basically the ratio of the corresponding sides. Basically what we just did, except this time you may not have to use all three. You can just use one side if they just want the scale factor. In this example, I'm telling you they're similar already, so you don't have to check all three or all five sides. Instead, I give you just one pair, and then you just write your ratio. So if I write this ratio, it's going to be 6/15. And then you always want to reduce the ratios for a scale factor as much as you can. I can reduce each of these by 3, and that gets me 2/5. Now, the one thing that's really important here, just like the similarity statement, in a scale factor, the order matters, because in this example, I went from small to large. All right, but I could reverse it, and I could go from large to small, and that would mean that my ratio or my scale factor would flip. So if I flip this around, I'd get 15/6, and reducing that, I get 5/2. And what that means is that the larger pentagon is 2.5 times larger than the smaller one. Now, if I went the original way, so that's this one here, then that means that the smaller one is 2/5 the size of the larger. All right, so that scale factor just tells you how much larger or smaller the shapes are in comparison to each other. In this particular example here, we've got two trapezoids, and they go ahead and tell you right away that they are similar figures. And notice they've got their similarity statement with that similar symbol in the middle, and you're going to use the fact that they're similar to solve for y. Now, to do that, we have to set up a proportion, and that's different than what we used to do in the past, where I'd give you two shapes and you'd solve for x or y, because these shapes may no longer be the same size, and that's the key thing you need to make sure you know about similar figures. Similar does not necessarily mean equal sizes, and so you can't just say one side is equal to another, because one may be really long and one may be really short. It just depends on the shape. So instead of just setting two things equal, we can use the concept of our ratios and our scale factors to set up proportions, and then we can cross multiply to solve. And that's what we're going to do here in this example. Now we're going to use the similarity statement in order to figure out which sides go together. Sometimes it's really obvious to tell, and sometimes it's a little harder, so that can be really useful. In this case, they tell you that AF is 12 units long, so here's A and F. Because they're the first and last letters, that means it has to go with V and Z. So I'm going to write a ratio using those two sides, so the 12 and then the 3y minus 1. So 12 over 3y minus 1. And then I'm going to set that equal to my other ratio. So that's going to be the other side that I'm given. So the 9 and the 6. And remember, because I started with the 12 on top, I have to start with the 9 on top. 9 over 6. And now we can go ahead and cross multiply because it's a proportion. And we'll get 12 times 6 equals 9 times 3y minus 1. To solve this, we just simplify using PEMDAS. 12 times 6, that's 72. And then over on the right side, we'll distribute. 9 times 3y is 27y. And then 9 times negative 1 is negative 9. And then this is just simply solving for a single variable. So add 9 over, we get 81 equals 27y. And then we can divide by 27. And when we do that, we get that y is equal to 3. And that's all I wanted, so we'd be done. Now we could plug it in potentially and figure out what VZ's length is, and then we'd be good to go. But in this case, they just wanted y, so we can stop. So just make sure you read your directions and that you answer all parts of them completely. One other thing that's going to be important, I'm not going to go through an example of it here, but if you have questions, make sure you let me know in class. But it is important to know that the perimeters of polygons will have the same scale factor as the scale of the sides. So if the scale of your sides is 3 over 2, then if you find the perimeter of each shape and write those as a scale factor, it's also going to reduce down to 3 over 2. So the perimeter scale factor is the same as the shape's scale factor. Good thing to know, and that can be very useful if you're having to find perimeter or a single side of a shape. Now, the last thing we want to talk about is specifically for triangles. So the other rules we've talked about could be used for any polygon, pentagons, hexagons, octagons, triangles. Here, this is going to be the rules for triangles to be similar. Some of these are going to look pretty familiar to you. We're just going to be using them in a slightly different way. Now, the first shortcut you could use to prove that triangles are similar is the angle-angle concept, so AA. And what this basically says is that if you have two triangles where there are two congruent pairs of angles, then automatically those triangles are going to be similar. So you don't have to know anything about the sides. If you know you've got two congruent angles, automatically those triangles are going to be similar. And I just went ahead and drew an example for you where we had two right triangles. Both had 25-degree angles and 90-degree angles, and because that fits our angle-angle theorem, then we would know that these two triangles are similar to each other. Okay? Now the second example is going to be familiar to you, and that is the side-side-side. And if you remember that from last semester, the difference is that last semester we talked about side-side-side to prove congruent triangles, so triangles that were the same size. Now we can use the side-side-side concept to see if they're similar by comparing all the sides' proportions. So the part here where it says if all side lengths are proportional is important. It's not that the sides are congruent, it's that their ratios are all the same. An example of this might be something like this is an 8, 4, and a 12. And then maybe this one here is a 16, an 8, and a 24. If I gave you these three pairs of sides, what you'd have to do is write them as ratios. So largest ones always go together. 12 over 24, which reduces to 1/2. And then 8 over 16, those are the medium-sized ones. So 8 over 16 reduces to 1/2. And then lastly, 4 over 8. That reduces to 1/2 as well. So because every ratio or scale factor is 1/2, they would be proportional, and so we'd know that they are similar. Now notice you have to have all three listed in order to use this side-side-side. And then the final one, side, angle, side. Again, very similar to last semester, except this time we're focusing on similar triangles instead of congruent triangles. So here you have to have 2 proportional side lengths, not all 3. The key is that you have an included angle. And when we say included, that means that the angle is between the 2 sides. That's very important. And this example might look like this. Maybe I've got this side is 20 and this side is 18, and then this side here is 60, and then this side here is, let's see, 54. All right, so then I could mark angle and angle. Just this picture alone, we know we have 1 pair of congruent angles, and then we have to find the ratio. So I'm going to set up the ratio of 20 over 60. If I reduce that, I get 1/3. And then I'm going to do the same thing, the 18 over the 54. If you reduce that, you also get 1/3. So in this case, our sides are proportional, and we have an included angle, the angle that is between the 2 sides, so that would make these 2 triangles similar. And you can still use the concept of vertical angles are congruent. That could help you mark something. So you're going to use some of last semester's stuff in this section, so hopefully it seems somewhat familiar to you. All right, and the last example for this section is just practicing using some of these concepts. It says here to solve for x. Notice that they marked 2 angles congruent, W and T, and then we're working with 2 sides. So this would be a side angle side situation if they told you they were similar. And we have to go ahead and set up a proportion. I'm going to have 8 over 10 equals, and then I started with the 8, so I have to start with x plus 6 over 2x plus 6. And then we could cross multiply. Now, one thing you want to make sure you do when you do cross multiplication is that distribute to every single term. So the 8 gets multiplied by all of the 2x plus 6. I always write it out first just to make sure that I have everything written correctly, and then I work through it. That way you don't accidentally skip over something. So this simplifies to 16x plus 48 equals 10x plus 60. And then you guys can solve from there. You would solve for x, that would be your final answer, and then you'd be done. All right, so you need to make sure you know how to tell if something is a similar figure, how to tell if there's similar triangles with our 3 shortcuts, and then how to solve for the side lengths or angles based on using proportions, and also being able to identify the scale factor. Those are the 4 main things for this section. That's it for today. Thanks for listening.